In progress.
Okay, welcome back. My name is Matthew Dipple with Airtight Engineering, and today in this video we're going to look at Module 3 of our Getting Real About Home Energy workshop geared towards real estate agents here in Saskatchewan. Let's get started. So Module 3, we're talking about Building Science 101. So a bit of an overview. The purpose of this module is not to make you experts in building science. We recognize that you're real estate agents and your goal is not to become a building science expert, but instead, the purpose of this section is really to outline some of the key concepts of building science that are going to be helpful for understanding home energy efficiency. So the key concepts that we're going to touch on in this module are, first of all, this idea of the house as a system. Then we're going to look at the house envelope. So that's the shell of the house. We'll look at airtightness and ventilation. And then finally, water and vapor. So how water and water vapor move through the air or through a building. And then an energy balance. So we'll try to make sure as we go that we tie all of these back to home energy efficiency. So a little bit of a motivation. Why does building science matter? Building science has the ability to help us explain when things go wrong and help us predict how to make sure that things will go right. And this is especially important if we're working on improving the energy efficiency of a building. We certainly don't want to accidentally create any unintended consequences. So I've got an example here. This is a family member of my colleague Stefan's, and this is something that happened to them. They have a family home and more of a cottage, and they removed a fireplace in this cottage. So here was their original cottage, and they ended up with water inside of the walls in the spring once they removed the fireplace. This had never happened to them before. Now all of a sudden the fireplace is gone and they've got water in the walls. So for them, it was quite baffling how this could be happening. And Stefan was able to deduce what was going on using his knowledge of building science. So what he discovered was their fireplace was actually drawing a lot of air with it. It was sort of the biggest hole in the envelope, and so the most air was leaking out of the house through the chimney of the fireplace. So you can see in the diagram there, we've got the big red arrow. So that's air that's leaking up out through the fireplace. So warm air in the space travels up the chimney and then exits the building. And that in turn, that air leakage out of the building ends up pulling some cooler air in through the gaps and cracks in the rest of the buildings. That's what was happening. Once they took the fireplace out, here's the new scenario. All of a sudden, what started happening was there's no big hole for the chimney for air to leak out. And so instead, warm, moist air in the winter started to leak out through gaps and cracks in the attic. And that warm, moist air had a lot of water held in it, which then began to hit cold surfaces in the attic, like the roof deck, to condense. And then in the spring, all of that ice that had been building up started to melt and began running down the inside of the walls. So it seems without building science, we might have no idea why this is happening, but understanding just a little bit of building science can help us understand some of these behaviors of the homes that we live in. So that leads us to our first concept, and this is the idea of the house as a system. This idea is basically using a holistic approach to understanding how a house works. And in this approach, we can divide out kind of three different areas. First, we can look at the components. So those are all the different parts and pieces of a house. Then we can look at the flows. So the flow of air through a house, for example. And then we can look at the outcomes. So what are the sort of qualitative outcomes we would like in our house? We want it to be warm, perhaps. We want it to be efficient, to be healthy, etc. So this idea of the house as a system is to understand that all of these, the components, the flows, and the outcomes, all work together in one unified whole. And so if we change one, we actually are going to change and make impacts on the others. Very much the same as a human body, right? If we can't just cut off a finger and expect there to be lots of blood left in the rest of our body. If it all drains out the finger, well, c'est la vie. It's going to impact the whole body. So same way with a house, we have to treat it as a system. So components, we could look at 4 different components in the house, and we're going to break them out separately to talk about them. But this whole point of the house as a system is that we're really understanding that they work together. So the first would be the building envelopes. That's the shell of the building. This is one of the most important components. This is really what makes a building, right? It's the roof, the walls, etc. And we've got the mechanical and the electrical. So these are all the sort of pipes and ducts and wires that are flowing through our house, carrying energy, air, water, all of those good things. Then we also need to consider, as part of the system, the occupants as well as the environment. So the people who are inside of the house and the pets and the plants and everything else inside the house actually have a big impact on the system. And then the surrounding environment outside we need to consider as part of that system as well. And those components together are going to greatly affect the flow of these 3 key components within a house. So the first is air. This is really important, obviously, because we want to breathe air. And so understanding not just how air moves through a house, but also what impacts air quality is important. Next would be water and humidity. So water can tend to be the biggest sort of thing that we face in our buildings that leads to degradation. Think of rotting, think of mold, think of mildew. That's water and humidity. And so we want to make sure that we're understanding how that moves. And then finally, energy and temperature. So is our house warm? How is energy or temperature, heat and cold moving through a house? And all of these flows end up to a large extent determining the outcomes. And so they end up determining the efficiency of our house, the comfort of our house, how healthy it is for us, and also how durable it is, how long it's going to last. So zooming in on one of these components, let's look at the building envelope. So the building envelope is, as I mentioned earlier, all of the exterior surfaces of the buildings. So this is the parts between you and the outdoors. It's not an interior partition wall. It's not a piece of furniture. It's just all of the shell of the building. And further, I want to make just a brief distinction between the building envelope and the thermal envelope. So we might have an area of our house that's inside of the building envelope. So in this slide here at the bottom, you can see the attic space, but it might be outside of the thermal envelope. So the insulation is following the ceiling line, whereas the attic is uninsulated and going to be cold in the winter and hot in the summer. So we can think of the thermal envelope as the boundary of all of the spaces that we're heating or cooling. And so sometimes it's not quite the same as the envelope of the building, which is sort of the outermost edge of the building. So there are actually 5 roles that we ask our building envelope to play. And I'm just going to play a short video here that explains what those 5 roles or 5 critical barriers are. And in the video, they're using the example of someone skiing, but to make it a little more Saskatchewan, you could imagine that they're maybe snowmobiling instead. So let's take a look at this here. Let's bring it up. Okay. All right. So one of the important things for understanding just that envelopes have these different processes that they fulfill in our building is understanding that energy efficiency isn't just adding more insulation. We can actually add a lot more insulation and still have a very inefficient house if we aren't getting some of those other barriers right. Another really key one is airtightness. You can actually lose up to 30 to 40% of the heat from your house due to poor airtightness. So you might have added all the insulation in the world, but if your house isn't airtight, it's not going to be efficient. And so we certainly need to make sure when we're talking about home energy efficiency that we have a basic understanding of these five critical barriers and the roles that our building envelope is playing. Speaking of air barrier, let's talk a little bit more about it. So this is a part of our building envelope that's maybe a little less well understood. Our construction industry has been doing a lot of great work in terms of the vapor barrier. For many years, we're probably all used to that clear sheet of poly, of 6 mil poly right behind the drywall. That's our vapor barrier. But there hasn't been as much attention given to air tightness necessarily. So this is something that we want to just touch on and stress because it is so critical to an energy efficient home. So the air barrier prevents air leakage inside and out of the house. And it's actually not just one piece. We can't just look at one piece of material and say, oh, that's there's the air barrier. It is actually a system of components. So it is in some cases, like this first top picture to the left here, I'll just put my mouse on it. There's the poly, which is being used as the air barrier, but also the window itself is the air barrier too, right? Because that's preventing air from coming inside and out. And so we need to make sure that the connection between all of those different parts of the air barrier is continuous. So here it's done with some acoustical sealant on this one. And on the bottom right here, we can see, in this case, the air barrier is actually taped plywood. So it's the structural sheathing, which has been taped, and all of any little holes in it have been taped as well. The window boxes have been taped, and then when the windows get put in, they will be taped to this as well. So in this case, our air barrier system is taped plywood made up of the sheathing, and then is going to include the windows and doors, etc. On the bottom here, we've got an exterior membrane. So here, the weather resistive barrier, often this would be Tyvek. Here it's a different, it's a Sega product instead, but this has been taped and it's being used as that air barrier. So we can see that it can look different in different buildings. It could be located in different parts of our assembly, but it must be continuous. That's something that's really important. Think of having a garbage bag, filling it with air, putting a twist tie on it, and then using an X-Acto knife to cut a bunch of holes in it. Is that air actually going to stay in the garbage bag? Well, no, it's not, right? We need to have it continuous, and that's where we use tapes, caulks, etc. So how does air move through a building? Air can actually move through a building through two ways. We can divide it into natural movement. So through windows, this is usually intentional, right? We open our windows to get some airflow through a house. It also moves through leaks in the building envelope. So as hard as we work, we aren't going to get a building perfectly airtight. And those leaks and gaps in the air barrier are going to contribute to air movement through the building. And then also it moves through some of the penetrations through the envelope that we make for different reasons. So chimneys, stovepipes, we have ducts, anything that's penetrating that building envelope has the potential to carry air. And we also move air mechanically on purpose. So we've got exhaust fans maybe in our bathrooms or kitchens that are moving air. We might have supply fans or ducts, or we might have heat or energy recovery ventilators with fans in them and ductwork to the outside where we're actually trying to move air into and out of the building. This picture just shows some of the key air leakage locations in a house. And I just want to point out that pretty much all of these, the vast majority, are occurring at junctions. So that's really where we see a lot of air leakage. So a big one is number 9 here, kind of right at the the base of the floor system, especially on older buildings. That's a big area of air leakage. Or like right up beside the chimney is another one that we see. If you have poor quality or just sort of so-so quality windows, they might have 3 panes of glass, but they might not be very airtight. So the airtightness of all the seals around that window is important too. So just an example of some of those leakage locations we might see in a house. And those can add up significantly. As I mentioned, can be 30 to 40% of your heating energy use in the winter if you're living in a very leaky house. So finding air leakage, we can use the blower door test. Remember, we mentioned this in module 1 and that this was actually a test invented in Saskatchewan in the 70s and is now used around the world. And this is the blower door testing unit here. It's basically just a big plastic sheet with a frame that fits in the door and some gaskets, and then it's a big fan. And attached to that fan, you've got a speed controller and also a pressure manometer where you can actually sense pressure inside and outside the building and see what the pressure difference is between the inside and the outside of the house. So what we'll do is we'll turn on the fan and we'll rev it up until the pressure differential is at 50 pascals, and then we'll measure the flow of air going through that fan. And then we can understand, if we measure the volume of the house, how much air is actually leaking out of the house at 50 pascals per hour. So then we can get sort of a standardized metric to understand, is this a leaky house or is this a fairly airtight house? The other thing that we can do, in addition to just getting a nice number that tells us if it's a leaky house or not, is we can also use a thermal camera or a smoke pencil or the back of our hand to go around while the building is under pressure or under a negative pressure and to feel for air leaks. So we'll be able to feel air rushing in through any little gaps and cracks. Or with a thermal camera, if it's cold outside, we'll be able to see those air leaks. So here's a picture of that here. Here's a door lock set, and you can see a big air leak right here just above that door lock set, kind of above the deadbolt. So it's showing up black because there's cold air that's rushing in through that gap because we are putting on the blower door fan. So this blower door is kind of simulating a big windstorm hitting all sides of the building at the same time, the air leakage that we might expect from that. So now that we've talked a little bit about air leakage and air that we aren't intending to come in, let's just talk about two types of ventilation in buildings. So the way that we used to ventilate houses and the new method of ventilation that we use today. So the old method was like this, a bathroom fan. So we would have bathroom fan exhausts and also maybe kitchen range exhaust as well. And these were not continuous ventilation. We would just turn them on whenever we take a shower or use the bathroom or we're cooking. We're creating maybe odors and maybe some particulate matter, and then also lots of humidity, and we want to exhaust that out of the house. We would turn on these fans. And what happens is when those fans exhaust air, fresh air needs to get pulled in from somewhere. And so it ends up coming in through all of the leaks and the gaps and cracks in our house. Sometimes in these older buildings, we would also have maybe a fresh air duct to the furnace and the furnace would help distribute some of that warm air as well. This is actually a picture of my bathroom fan. So there you have it, 50s house. The new method of ventilation is far superior in many ways. So now we're using a unit that's called an HRV or an ERV. That stands for heat or energy recovery ventilator. And this is now balanced ventilation. So this unit is designed to run all the time, slowly, just in the background. And it's providing constant fresh air. So instead of just waiting till you take a shower to get some more fresh air into your home or needing to open the window, which is great in the summer, but less helpful in the winter, we actually get constant fresh air. So the HRV is balanced as well. So it's not pulling air through the gaps and cracks. So this is really important as we have airtight houses, is there are fewer gaps and cracks to pull air through. And so this unit brings in the same amount of air as it exhausts. So it's got two fans in it now. The other big thing about this is it's got a heat exchanger in it. So the air that's leaving the house drops off its heat in the air that's coming into the house. So the two air streams don't mix, but they exchange heat, and they can actually save 50 to 90% of that heat. So you aren't having to reheat air from scratch all the time. So let's take a look at another video from the BCIT at the operation of one of these units. Okay.
Drinking coffee every day.
Drinking coffee every day. Rock on. Okay. So there's a quick description of what a heat recovery ventilator does. And I will just note the difference between a heat recovery ventilator, or an HRV, and an ERV, which is an energy recovery ventilator. So an ERV is able to recover both heat and humidity. So this is actually quite helpful in Saskatchewan. So lots of times we would recommend ERVs to our clients because it's dry, it's cold in the winter, and so if we can recover some of that humidity from the air, it's actually going to make it less dry in our houses in the winter. So we can see the benefits of this new method of ventilation. We get better control over the fresh air. We get to distribute the fresh air into our houses more evenly. We get more continuous ventilation. We can have the opportunity to filter that air. We get to recover a lot of energy from the ventilation air. And so it's overall, it's just a great strategy and a pretty simple machine, really. It's basically just a heat exchanger core, which has no moving parts, and then two fans and some dampers. So it's a great option. I will note in the video, they're showing the HRV located in the attic. We don't really do that here. We would normally put them in a mechanical room. So that's it for ventilation. Let's just talk briefly about heating energy balance. So now we're looking at the way that energy moves through a house, and you can imagine how important this is for energy efficiency, because if you don't understand how your energy is entering or leaving your house, how can you control its use or be more efficient in your house? So this idea of an energy balance is is basically saying, in order to keep our house warm in the winter, we need to replace all of the heat that that house is losing. And so to calculate how much heat it's losing, we add up these two main types of losses. The first is transmission loss. So that's the heat that we lose through the floor, the walls, the roof. So, you touch the wall and it's cold. That's because it's losing heat to the outside. And the second is ventilation heat loss. So this is through all of that air leakage that we were just talking about, and also through incomplete recovery from our ventilation system. So our HRV might be able to recover 50 to 90% of our heating energy from that air, but whatever percent it can't recover, we need to replace. On the other hand, we have a couple of gains, heat gains, that help us out and reduce the amount of heat we need to provide. The first is solar gains. So the sun coming in, shining on things in the house, warming them up. That's some free heat for us. And then also internal gains. So we've got the picture of the people dancing, or I don't know, doing Zumba. I'm not sure what they're doing, but they're generating heat as well. Fun fact, each person generates, usually with normal activity, about 130 watts of power output. And so that results in heat inside the house. So it's like, 1 1/3 100-watt light bulbs being turned on. That's how much heat you would be generating. So those are some of our heat gains. So we get to subtract that. It's free heat. And then whatever additional heat is not covered, our heating system needs to make up. So this is what that balance looks like. So you might be wondering, how much heat do I need to provide for my house to stay warm? And the answer is enough to complete the balance. So we've got our little balance beam. We can see our losses on the one side, our gains on the other, then our heating system, number 5 there. That's the remainder that our heating system needs to make up. So how this relates to energy efficiency is this begins to show us how we can make our building more efficient. We've got a few options. We could reduce the transmission losses. We could reduce the ventilation losses. We also have the option to increase some of the gains, right? So if we could increase some of our solar gains in the winter, that would also help make our house more efficient. So this is part of why a heating energy balance is so useful. And this is the basis, this is the central calculation that every fancy energy modeling software is doing, is just this heat energy balance. When we look at cooling, we actually have the exact same thing. We've got an energy balance for cooling. So to keep a house cool, again, we need to balance heat gains and losses. Only this time, those two gains that were helping us in the winter actually hinder us in the summer. So now they're on the other side of our balance. So any solar gains that we're getting and any internal gains from people or pets or what have you, those are actually working against us, and we need to expend more cooling energy to offset those. And the last kind of aspect of energy movement through a house that I want to touch on is an idea called thermal bridges. And these are something that we haven't necessarily given enough thought to in our construction industry, specifically the residential construction industry. Often we'll put in a lot of insulation, but we won't think of the spots where we've got breaks in the insulation. So a thermal bridge is anywhere where there's a break in the insulation layer. So this could be a footing, concrete footing. This could be a chimney, a brick or stone chimney poking up through the insulation, conducting heat. Could be the studs in a wall. And they can have really big impacts. So they impact our energy use. They can also create cold spots, which lead to moisture damage, potential for mold growth, etc. In this picture here, this thermal bridge that we're seeing is, you can see the sort of purple aura happening here. This is in a basement. That is the footing. So there's probably insulation on the outside of the foundation wall down to the concrete footing, but not underneath the concrete footing. And then same thing on the basement floor. There's insulation up to the footing, but not underneath that footing. And here we can see that very clearly, that there's extra heat loss happening through that footing. Okay, let's talk a little bit about water and humidity movement. So what does this have to do with energy efficiency? You might be wondering. Energy Heating balance, it's really obvious what that has to do with energy efficiency, but what about water vapor? Well, the interesting thing is this is actually kind of an effect for us of energy efficiency. Often, when we focus on efficiency and improving the efficiency of a building through further airtightness, through more insulation, we end up addressing moisture issues that are happening in a house. So, a well designed, efficient home should also become a healthier home with fewer water issues. This is a picture. This is a room that I stayed in up north in a community in northern Ontario, and we see some moisture issues happening here. This is actually not leakage from the roof. It's not from rain. This is because there's not enough insulation in the ceiling. And so when someone's sleeping in the bed below, they're breathing, they're creating humidity, and those ceiling tiles are too cold. And so when that humidity gets in contact with the ceiling tiles, it actually creates some condensation within the tiles, and then this very alarming looking staining on them. So if we made this building more efficient by adding additional insulation into the attic, chances are we would solve that moisture problem at the same time. Here's just another example of vapor damage. So this is my bedroom in my house. It's the master bedroom in my house. And you can see some bubbling and cracking, peeling paint on the ceiling. I noticed this start to develop over a period of months, and I wasn't sure what was going on, but I used some building science superpowers and a little bit of just elbow grease to crawl around in my attic and do a bit of an investigation. And what I saw was that there was damage to the vapor barrier up there. The vapor barrier, it's a 50s house, and it happened to be wax paper, so pretty easy to damage, go figure. And there was only a small amount of insulation present on top of this particular spot in the attic. And that insulation was of poor quality, as well as wood chips and a bit of blown in fiberglass too. And this is what it looked like in the attic. So here I've moved some of that insulation away. There wasn't much to begin with. And you can see this brown stuff is wax paper, and then this white stuff is the damaged wax paper. So it's had some damage to it, and there's maybe some like a tear in it as well. And so there's moisture that is now condensing in that ceiling because it's cold. Some moisture is able to get up through the ceiling as well. And so it's causing that paint issue. So I could just repaint that spot, but I would end up with the same problem happening again over and over unless I do something to fix this. So I did that. I actually repaired the vapor barrier. I added some more insulation, and now I can repaint safely without worrying about it coming back. So I just share that to show that I might be adding insulation to my attic for maybe an energy efficiency perspective, but I'm also going to make it less likely that I have moisture issues once I do that too. So a little bit more about water and humidity. It's important to realize that we generate humidity as building occupants. In fact, we generate a lot of humidity. We do it through cooking, through breathing, showering, watering plants, doing dishes, etc. And all of that humidity needs to go somewhere. When it's cold outside, we have the potential for that humidity to hit cold surfaces and to condense on them. So that's something that we could see. The other thing that we want is we really want to keep the humidity in the air in our house in a comfortable range. So ideally between 20 to 30% relative humidity and 60%. That's kind of our ideal range as human beings. So we need to make sure that we're dealing with excess humidity or also dealing with humidity that's too low as well. So cold air, the reason that we can see condensation is cold air holds less water vapor than warm air. And when warm air gets cooled down, it can't hold as much water. And so some of that water has to condense out into liquid. So think of the cold inside of a window. We've probably all seen this condensation happening, or your favorite beverage can on a summer's day, right? It starts to sweat and condense on the outside. So this can be damaging when it's happening on a window because you can start to create mold on the windowsill or rot. It can be even more alarming if it happens inside of a wall and you start to create mold and rot inside where you can't actually see or deal with it. So just a quick note on vapor barriers. We do not want any moisture condensing inside of our building envelope. And so we need to make sure that we're using both the vapor barriers and air barriers to stop this condensation. So we kind of use those both in tandem. We don't want any air leakage that's carrying moisture, and we also don't want any moisture just diffusing through the materials in our house. So we want to somehow stop it with a vapor barrier as well. And our other tool to control any potential moisture condensing inside of our building envelope is to manage the humidity in the air in the house, right? So to make sure we have good ventilation, we don't have an excess of humidity happening. The last two areas that I want to touch on briefly is just to present this idea of how occupants and environment impact our house as well, our house as a system. And especially in terms of efficiency, occupants have a huge impact, right? So imagine the people, the pets, and the plants in a house, they're going to impact all of those flows throughout our house and the outcomes. So whether that's energy use, whether that's the humidity that's generated, whether that's air quality, the habits of our occupants play a huge role. So we've got two houses here. The top left is our green thumb. This is actually my spare bedroom of a number of years ago. I was starting way too many tomato plants for the garden that my wife and I tend. And this was causing some humidity problems, as you can imagine, and also was greatly increasing our electric bill due to all of those grow lights. And then the bottom right, we've got the blockchain miner, made up person who is just mining up a storm. It's got a ton of processors running. And you can imagine that that would generate a lot of heat that could lead to some thermal comfort issues. And it's going to use a lot of energy as well. So we can't actually consider a house and how it's performing without considering the occupants too and how they're interacting with that house. Environment also plays a big role. So let's imagine our Bitcoin miner and they're located at the North Pole. Well, that heat from all those computers running actually is going to help a little bit with their heating costs because it's going to offset some of what their furnace or their boiler or wood stove needs to provide. Versus if they were located in, say, Death Valley, a very hot location, that same Bitcoin miner's house is going to require even more air conditioning than it needed before. And they're actually sort of having to work against that extra heating load to cool their space. So we can see that the environment has many factors which impact the efficiency and the energy use in our houses. So the temperature is one I mentioned, also the humidity outside. We have different problems in Saskatchewan than they do in BC because we have different levels of humidity. Cloud cover, air quality, all of those things determine our potential for generating energy, how much energy we're going to use in our house, etc. So just to kind of bring that point home that the system, the house as a system includes not just the components and those flows, but it also includes the occupants and the environment surrounding the house. So, in summary, our buildings are interconnected systems. As much as we would like to treat them just as discrete components that we can swap in and swap out, we need to understand how those work together, and that when we alter one component, we're actually very likely to impact other aspects of the house. And finally, building science underpins our energy efficiency measures. So, in order to do energy efficiency well in a house, we need to understand some of these basic concepts as to how a house is functioning so that we make things better instead of inadvertently making things worse. All right, thanks so much. And I look forward to seeing you in Module 4.